Hello everyone. In this video, we'll be talking about a simple yet interesting topic, number system. When you type in Google, what is a number? This is the exact definition you receive. A number is an arithmetic value used for representing the quantity and used in making calculations. Simplifying that, basically all those 1, 2, 3, 4, 5, 17, 18, 19, all these are numbers, right? These numbers have their origins from Egypt and Babylonia, like hundreds and hundreds years ago. Egyptians and Babylonians basically had their full-fledged number system, which consisted of these whole numbers as we know them today, and a couple of rational numbers. Now, what is interesting is that this number system can be divided into a number of parts. So the first one we talk about is the number 1. When someone tells you to count, you start off by saying 1, 2, 3, 4, 5, so on, right? 1, 2, 3, 4. These are numbers that come to you naturally. When anyone tells you to start counting, you never say 0, 1, 2, 3, 4. You always start with 1, 2, 3, 4, right? These are therefore known as natural numbers. Or you can say numbers that come to you naturally. Now, these numbers go on from 1, 2, 3, 4, so on till positive infinity. Now, you'll say infinity is infinity. Why positive or negative? You'll see when we progress, right? Then there are one more type of numbers, one more set of numbers that come across when you add a zero, just 1 0 to this set of natural numbers. So 0, 1, 2, 3, 4 till positive infinity again. These are whole numbers. The major difference between natural numbers and whole numbers is just that natural numbers start from 1 till positive infinity, but whole numbers include 0 other than other 1, 2s, and 3s and 4s, right? So these were whole numbers. Next, there must be a number, don't you think, between 1 and 2, 1 and 2. Let me draw a number line here. So we are catering to the fact that if this is a number line, it has a 0 right here, and it has a 1 right here, and 2 right here. There must be something in here in between, right? Because if there wasn't, we could have just written it like 0, 1, 2, 3, 4, 5. Well, even these numbers have space between them. There must be something lying here. What is that? You must have heard of decimal expressions. Expressions like 1.1, 1.0001, 1.2, 1.3. These are decimal numbers, right? But neither do they come in under the category of whole numbers because they have this decimal here, nor natural numbers, right? If I say 0.1, the question is, where does this lie? So here we come across another category of numbers. Look closely at this number, 0.1. This is basically 1 divided by 10, right? When you divide 1 by 10, we know that if the number of zeros in the denominator gets replaced by the decimal place, the number of decimal places after the point, right? So if there is 1 0, it becomes 0.1, 1 decimal place. If it's 1 upon 100, it becomes 0.01, 1 upon 1000 becomes 0.001, and so on, right? This just continues to happen. As we increase these zeros, these numbers increase. So with this, after all, can be written as 1 by 10. Now, this is a rational number. Rational number. Now, something that we should understand here is that we're still dealing in positives here. It's plus 1 upon 10, plus 1 upon 100, and plus 1 upon 1000. This is a rational number. And how do we define a rational number really? We just say they are in the form of P by Q, where Q is not equal to 0. This is because division by 0 is undefined. We'll talk about this in another video, while division by 0 is undefined. But here, all we're concerned with is that rational numbers are represented in the form of P by Q, where P and Q are integers. This is important. This P and this Q can be any integer. So there are basically integers. Now here we come across another category, integers. Integers are basically the positive and the negative form of natural numbers plus 0. So the natural numbers include 1, 19, 1, 0, 1, 5, 6, 7. All these are natural numbers. These are integers, and as well as their negative form. Minus 1, minus 19, minus 101567, minus 468, minus 509. All these are also integers. 1, 2, 3 to positive infinity, and minus 1, minus 2, minus 3 till negative infinity, and 0. All these are integers, right? So basically, rational numbers, coming back to rational numbers, are represented in the form of P by Q. Q is not equal to 0 because division by 0 is undefined. And an important criteria here, P and Q both are integers. That means that rational numbers again can be positive and negative. So 7 by 8, 9 by 10, 111 by 245. All these are rational numbers. Again, minus 1 by 5, minus 4 by 7, even these are rational numbers. So rational numbers again are both positive and negative. Then we talk about another category of numbers, irrational numbers. Before we start with irrational numbers, it is important to understand that all integers, all whole numbers, all natural numbers are rational numbers. The question that arises now is that how is minus 1 a rational number? It is not in the form of P by Q, it is just minus 1. There's nothing in the denominator. Well, it is important to understand that such a number can always be represented as minus 1 by 1. Because if something is divided by 1, it remains the same. Minus 2, minus 3, 5. 45, all these are rational numbers. Why? Because we can represent -2 as -2 by 1, -3 is -3 by 1, -4 is -4 by 1, 45 as 45 by 1, same thing, right? Now we talk about irrational numbers. Irrational numbers are non-terminating and non-repeating. I'll just write that down. These are two important terms you need to understand. Non-terminating and non-repeating. What do you mean by terminating? These are basically the types of decimal expansion. Right? Just this. Non-terminating. Terminating means something that ends, something that has an end to it, right? So when I talk about non-terminating, it is basically, for example, 4.10. That's it. It's 4.10. Done. Finished. It's ended. It's terminated. It is not going any further. This is terminating. So similarly, 5.2304. This is terminating, right? Again, 6.16, terminating. So terminating decimal expansions are rational numbers. But if there is a number, for example, pi, it's 1.4142 something, 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 so on. This just goes forever and forever. There's a whole book that has the value of pi and it still does not end. This is non-terminating. It's non-terminating. And this is why it is irrational. A number which has a terminating decimal expansion is rational because then it can be represented in the form of p by q, right? But a number which has a non-terminating decimal expansion is irrational. What about repeating? Repeating, for example, 4.55. This is terminating and repeating. If it is terminating, then again it is a rational number. What about 4.5555 and so on? Or 4.5 bar? This is also a rational number. Something that has a bar on top, that means it's repeating itself again and again. For example, 36.12 bar, that means 36.12, and so on. It forms a pattern, it's repeating. That is why it is again a rational number. It's rational, even this is rational. But talking about non-repeating, if there is a number, for example, 4.6748392169, so on, this is an irrational number. It's not repeating itself, it's just going on and on and on. It is not, we don't know how it is going to end. It's not going to end because it's an irrational number. Similarly, if we have 4.501001, 0001, 4 times 01, and so on. Is this a rational or an irrational number? This is an irrational number. It forms a pattern, but it does not repeat itself. There's a difference between forming a pattern and repeating itself. There is 1 0, then 2 zeros, 3 zeros, 4 zeros. There's going to be 5 zeros, 6 zeros, 7 zeros. We know that. But we cannot put a bar on 0 1 because it's not 0. It's not this 0 1 0 1 0 1. No, this number of zeros is continuously increasing. It forms a pattern, but it is not repeating itself. And that is why it is non-terminating and non-repeating. Therefore, an irrational number. So basically, irrational numbers are non-terminating and non-repeating. Whereas rational numbers, on the other hand, are terminating and repeating. If they are terminating, they are rational numbers. If they are repeating but not terminating, even then they are rational numbers. So for rational numbers, even if one of these situations is true, then it has to be a rational number. But for an irrational number, it has to continuously move on and not end. That is non-terminating, and with it, non-repeating. Both statements have to be satisfied when it comes to an irrational number. Now, again, we'll just sum this up. So there is your number system, right? This is a number system. I'll make a flow chart out of it so it's easy to understand. First type of numbers, whole numbers. Second type of numbers, do it in a different color, wait. Yep. Second type of numbers, you have, I just reversed it. Okay, never mind. I'll go this way now. Natural numbers. So natural numbers are basically the first type of numbers, and whole numbers the second ones. Natural numbers. Third, we have integers. Then we have rational numbers. And then we have irrational numbers. Right. So all natural numbers are whole numbers. This is 0, 1 to positive infinity, right? So all natural numbers are whole numbers. All whole numbers are integers. These are 0, 1 to positive infinity, minus 1 to negative infinity, right? All integers are rational numbers because these are in the p by q form. Q is not equal to 0, and these two right here are integers, right? And there is a difference between rational and irrational numbers, so you don't say that all rational numbers are irrational numbers. And all these types of numbers here, whole numbers, natural numbers, integers, rational numbers, irrational numbers, all these types together form real numbers. Why real numbers? Because these do really exist. Now, to contradict these numbers, we have another type of numbers, imaginary numbers, which we're not going to discuss in this video. Imaginary numbers are basically some things that don't exist. Imaginary numbers don't exist. We've just made them up. I'll just give you a couple of examples for you to ponder upon. For example, if you have root 1, okay, to say root, let's keep this simple, root 169. 13, we all know. Root 114, 12. Root 256, 16. We know this, right? But what if I say root minus 169? The point is 13 into 13 is 169. Minus 13 into minus 13 is again 169. So where did that root minus 169 come from? There is no possible way that this 13 can be made into 169 minus 169, right? Because according to the sign convention in integers, this minus and minus turns to plus. Plus and plus again turns to plus. There is no way that the square of some number can be minus something, right? Again, there is no way that we can end up to root minus 114, or for that matter, root minus 256. So these are imaginary numbers that don't really exist according to other sign conventions that we've already discussed. Now, right now, what we are concerned with is the number system when we have natural numbers that come naturally to you, whole numbers that consist of all natural numbers and zero, integers that consist of the positive and negative form of the natural number, that is 1, 2, 3, 4, and minus 1, 2, 3, 4, again till positive infinity and till negative infinity respectively, and also zero. So basically integers constitute of all whole numbers. All integers are rational numbers. Then you have a conflict, rational numbers and irrational numbers. And all these 5 types here, 1, 2, 3, 4, and 5, are real numbers because they do really exist.